Hello, welcome to another coding session. We're going to continue with Bangalang, surprise, surprise. And we're also going to continue with, in the last session we started working with SIMD. We got something working with a nice frame rate upgrade, which is really nice. The problem though is the egregious code that I wrote. Some of you may in particular be wondering about this loop that I made. Because we're saying like if there's more than one thing we want to copy, say there's 8 things we want to copy, then it should go into this loop twice, right? And sort of move them twice, but the destination and the source are not changing during this loop. There's all kinds of ways but this is wrong. So I think really what I ought to do is like move this code up to the assignment. Where is it? Generate assignment. So there should be here like a generate assignment float array. Oh, we should get rid of this code that we don't need anymore. Really, this is where that code should be. I think we should just like do all of our assembly in here instead of, I tried to make this copy a bit smarter, but I think that was the wrong approach. I think I should leave the copy the way it was, and we should be more intelligent up here. And while we're at it, we're going to try and support slices as well, because you should be able to, like slices should use SIMD as well, which is the same as an array. It's the same kind of thing. So what do we need to do that? Well, let's maybe let's just like copy this fancy code. I say fancy, this dodgy code that I wrote, and I'll just revert that. I think that if I just go like this, I think that's basically where it was. Just doing a simple scalar move, so moving a single float. And let's get rid of these count parameters from our copies. I'm just going to paste this in like here. But another thing I noticed is there's like this thing here where it says, should we change our copy to registers to copy to non-immediates? No, I think actually what we're doing now is kind of quite a big beast. So maybe my glasses are getting all foggy. Maybe we'll revisit that at the end, if we have time, which we most likely will not. So what are we really trying to do here? We have this copy to register business. We need to fix up a few errors. I think this is going to be where, we were passing a count in, but we don't need to anymore. And this should be test source. So instead of doing this copy to register, let's just move this up here, I guess. This is copying 4 floats into a register. And because of that, we're going to need like an RHS register location, which I guess will be using the register num and the element type node. And the that'll be the left-hand side, and the right-hand side is register num +1. See, this is the same as we did down here. So then, the precision is just a variable here. So we're going from left-hand side location to left-hand side register location. And same with that. And instead of passing in a parameter, we just put copy. Okay, I think that should be happy in a second. Yeah. So that's going to move 4 floats in. And then we need to do whatever operation it is. This will be done with the register locations. Oh, that's already a register location. I am kind of surprised. I thought this one didn't need to be a register. I thought we could just have a memory location, but it seems like that's not the case. So we're just going to start like with the simple case, and I'm going to write some tests, and we're going to do some almost test-driven development. Wow, fancy. So we don't really need that. We've sort of taken care of this loop. So this shuffle and move business is for doing individual ones. So like for our tests, what I'm thinking is I'm just going to create some general tests. And let's do like add assign 1. And we'll say like array 1 is an F32 with just 1 element. And we'll make that element a 1. And then we'll make an array 2 that has a 2. And then array 1 plus equals array 2. So that's our operation that we want to test. And then array 1, 0 should be 1 plus 2, right? It should be 3. So this is our initial test. I might just isolate it. I would like to have a nice way to isolate tests. Like, ideally I'd like to have, some command line arguments, and so there's a value tests. I think I can just disable all my value tests like this. Yeah, it'd be nice to have some command line arguments like, when you run the compiler, just say optionally run tests, or, run an individual test by name, something like that. But at the moment, I'm just commenting everything out. So of course we have a bunch of errors. I almost don't really want to run the main program. The main program is going to probably crash at this stage. Okay, so we've copied our data into these registers. We've done the vector add. Now we want to kind of keep track of where we are and how much processing we have to do. So we do have this length, and we'll have to get to this in a minute, because when we get into slices, we're not going to have this length available at compile time. So we're going to have to do probably copy this code we do here as assembly. So at runtime, it does all this. But for now, we can just say length, and we can just say, something like for index 0, index is less than length, index plus equals 1. I don't think we're going to maintain an offset. Like I am in the back of my mind thinking like, how do we need to do this in assembly? Like if we can do this code as close to what we would need to do in assembly, then the assembly version would be not so bad. And the reason for having 2 versions is because the assembly version is going to require like looping and complex flow at runtime. And for short vectors, I'm optimizing for my use case here, which is maybe something you shouldn't do in a language, but I'm expecting that a lot of the time, like you're doing 3D simulation or something like that, you're going to have vectors with 3 elements or maybe 4 elements. So I would like that to be super fast, not to have to loop or anything, because it's not really necessary. And then for really long arrays, you're going to have to loop, I think, because the alternative is that, you print out this instruction like in assembly, like 100 times, and now your executable is going to get really large if you do, you know, a bunch of operations. So for every element, the basics of it is that we're going to do a move, right? Des to source. This is where we're going to have to like change this. So I might actually even do this old trick. I only learned it recently. But this is because parameters in Odin are immutable. This basically is declaring that I want them to be mutable. I want to be able to change these things. So this one is the LHS location. And this is the LHS register location, because that's where, in this comment business, I guess this is like copy. Because the LHS register location is where the result of our add or our operation is going to be, right? It's going to be in the left-hand side register. So we're saying copy the leftmost element into the left-hand side location, the original left-hand side location, because this is an assignment operation, right? We're assigning to the left-hand side. Okay. So now we say if index is less than length -1. So we're just going to cut like all of this out. That means that we have more elements to process, more elements that we want to copy out of our result into our left-hand side. So this is like the shuffle. And this is shuffling the left-hand side register location. Actually, I think we need to put that in twice. Yeah. So that's just going to move everything to the side. I explained that a bit in the last video, so that when we do this, so when we loop around and do this copy again, it'll be the second element that we're copying, but we don't want to copy it to the same location now, do we? So we need to change the offset of this. We need to add element size to it. Okay. And I don't really want to maintain this index, because this is going to be, like when we go to assembly, this is going to be an extra thing that we have to maintain. If we already have this, I think basically instead what I want to have is somewhere I want to have like, where is the end? Where is the end? And that is the, I guess, the current offset plus length times element size. That's like so that should be the address at the end. So I guess we could even go, maybe it's better to go like this. So it's the left-hand side location, but we increase the offset to go, basically to go to the end of the array, right? And now we say for element index dot, while that is less than the end offset, that means we have more to process, right? And while this is less than end offset minus element size, I don't know if this is, we might change this in the future, but this should be effectively the same loops, but without having to maintain this index variable, because we're incrementing this offset anyway, so we can use that. So the question is, does that work? It does not like that. I guess I need to do plus equals, don't I? It would appear that seems suspiciously like an infinite loop. So it might be that it never comes in here. If end offset, the offset is less than end offset minus element size, yeah, probably what I want to do is have this outside, because yeah, especially in the case of like an array of one element, we never need to shuffle, right? So we should actually never go into this if statement. There we go. Wow, it actually worked. I'm kind of surprised that these triangles are moving properly, since I just changed all this code and like totally, I thought I would have messed it up. Oh no, maybe for that use case it is. Here's the code right here. Yeah, it is. You know, we put two memory addresses in the here, and then we add them together. We move the first element to here, shuffle, second element to here, shuffle, third element to here. Yeah, it's perfect. Okay, great. Yeah, that is fantastic. We actually need more of a loop. So my idea is that this kind of code that does not include any loops should work up until you have 7 elements. Or should I just make it 4 elements? That is kind of what I'm optimizing for, isn't it? Like beyond that, I'm just going to loop. Okay, that'll keep this code nice and simple, I suppose. So now, yeah, there is the case where we might not have a length, or the length is above 4. So I'm going to go length location is that. And then we need to say like if length location type is immediate. Remember, immediate is like a hard-coded value. So that if it was an immediate, that would mean that we can get the value and convert it to a number. And if that length is less than or equal to 4, then let's do what we just did. Yeah. So this should cover arrays with length up to 4. If we have longer arrays or slices, we need to do something different. Yeah, this is exactly the code I was looking for. Let's allow slices. So now we are allowed to do you know, plus equals, minus equals, all those things with slices. Probably in generation we did change when that's called, so that it will go in there for slices also. So now it should work for slices. I think I would like to add a few more tests before we go further, actually. So let's just confirm that it works with 2 elements. Just increase them like that. So these will be even, and these, yeah. I'll add 1 each time and 2 each time for these. So then that should be 2 plus 4. So that should be 6. And then we'll go to assign 3. 32, 6, 2, 2, and that'll be 9, I guess. Oops. And then we'll do one more, which is 4, because remember we were supporting up to a length of 4 with our non-looped array. For arrays up to 4, we do not use loops, like so. So does it work for all of those? Yes. There were no errors. Awesome. I'm curious if we... Oh, wait a minute. Tests are turned off. Ah, but it does actually work. Yeah, this test looks like it was just doing 2. This is a 2 element. Because the tests are in a map, the order is like non-deterministic. And this test.asm is just going to contain the assembly for the test that was run last. In this case, it looks like it was one with 2 elements because it's copying out one element, then shuffling, then copying out the second. But all the tests still, I'm glad I figured out that they were not on. Otherwise, we would be assuming everything was fine, when indeed it is not. So this is going to be the tricky part. We need to be able to do this for assembly, and we need to like loop. So actually here, we need to return, right? Or is it within here? Yeah, if we get into this if statement, then when we're done, we need to return because we don't want to do all this assembly stuff here. So we want to do the same kind of stuff. And I guess we still want those locations, but these, yeah, we still want those as well, but we're going to need to be able to modify these somehow. So I guess these we can take out, we can put them up here, right? We always need those. But the left and right hand side, we need to be able to modify. So I think I'm going to make, I'm going to make some more registers which hold the address of these locations. So that would be I have this like unknown reference, because they're storing a reference, an address as a reference. We can reuse these register numbers because these registers are going to be general purpose, and these registers are SIMD registers, so they're different registers, you know, these SIMD ones as opposed to general purpose ones. And then the LHS location is like treating this location like memory. So I think the way to do it is like this. So then as we modify, so yeah, so these are addresses. We actually need to put the address in there, right? That would help. Oh, it's not just a copy, is it? It's like a reference. How do we do our references? Like this. Load effective address. So we need to load the effective address of the left-hand side location into our address location. So now this is holding the address of our left-hand side. And we're going to update our left-hand side location variable to point at this so that we can change this address, you know, move forwards in the array as we go. So we'll do this again for the right-hand side. Okay, so now we have left and right-hand side we can change. I thought I made this, I thought I put that somewhere where it could be accessed. Yeah, it's up here. Okay, it's not complaining anymore. That just needs to be a regular assignment. Okay, so now the other variable I want to make is like a limit. A limit variable, so we're going to make it, put that in a register. This one is going to be +2, so it doesn't conflict with the other ones. And this one is a, I guess this one's going to be like an I64. I feel like maybe this variable we can put up here. And reuse. So that can be index type node. And that wants to store, like, because we're going to maintain these addresses, right? And we're going to move through the array by moving this address forwards. So this here I want to be basically the end of the array so that we can do comparisons with it and we know when to stop. So we need to start, I think we start with the length. Limit location, length, location, oops. So that should copy the length into it. Then I want to, so I don't actually want this to be the end of the array. I want it to be the end of the array -4, because up till that point, we want to be doing our move UPS. Which interestingly, we never actually do here. We should potentially update that. Like if the length is 4, then we shouldn't do this individual stuff anymore. We should just do a move UP. Okay. Actually, before we go any further, let's do that. We can just do a special case, you know, if the length is 4, then we do a move UPS, and that's from the left-hand side register location to the left-hand side location. So that's just going to do copy all 4 of them at once. Otherwise, we do this loop. Okay. So yeah, we kind of want the equivalent of this, but in a loop. Actually, let's just check if that still, yeah, that still passes all the tests, good. So we have the length, and so I want to subtract 4 from that. Subtract 4 from the limit location, and then multiply it by the element size. So then that gets like the length of the array in bytes minus the last 4, and then we want to add the LHS location. So this limit location should be relative to the LHS location. It should be like where we stop, so we can compare these two. Okay. So now we're starting a loop. So we need a vector assign index, and so it's like vector assign, I'll call it the multi-loop. So we're starting a loop. I mean, I put a label here so we can jump back up to the top. We copy in. Now we do our comparison. Well, we copy in, yeah, we do our comparison. We compare the limit location and, yeah, these two. So if the limit location is greater than, no, if the left-hand side location is greater than the limit location, then we want to jump. So we jump if greater to what I'm going to call the single loop. Yes, we don't need these actually. Okay, but if we did not do that, that means that we can copy all four at once, which was this. From there to there. Yes, that's correct. And then after that, we would add to our left-hand side our addresses, update our addresses. So we're moving forward in the array now, and the amount we move forward by is that right? So we move forward by an immediate, which is 4 times the element size. So no, that was wrong actually. We want to put this on the outside. So that should move us forward far enough that we can then do our operation with the next 4 elements. And after that, we would jump back up to this loop. Jump to that label. And so then we do another 4 and another 4 until we get to this point where it's like, okay, we don't want to do 4 anymore. We've effectively done our last operation, and that's where we want to do our individual moves out. So actually all of this so far, well, I guess it will happen with the 4 element slice. So then down here we want to have our label, which is the single loop. that's where we start the single loop. And that's where we want to do just like a single move. Yeah, it's this business here. So we want to do a single move, that's correct. And then we want to do a comparison, something like this. And skip to end if we're done. We're going to have to change our limit location now though, because it needs to move forward a few elements so that we really don't stop until we get to the end. Yeah, so it's some place we need to change this limit location. And where would that be? It kind of needs to be after we jump out of the multi-loop. Like after this jump, but before we come into this loop. So actually I think we're going to have like another label here. This is where we initially jumped to. And here we need to add to our limit location. And how much do we need to add? Is it 3 or 4? If we add 4, that means we need to get right to the end, right? Do we want to get right to the end before we do this jump? Yeah, I guess we do. We need to move them all. So we would add basically this, 4 times the element size, to our limit location. And so now this loop will continue. So because we're going to have like a jump down here. So this loop will continue until we compare and see that we're at the end. And then we will jump to the end label. This is complicated assembly, I have to say. So we're going through this single loop. We're doing a move. If we're not done, no, if we are done, we jump to the end. Otherwise, we don't just jump back up. We need to do our shuffle first. So where's our shuffle? This guy here. We need to do a shuffle of the left-hand side, that's correct. And then go back up to the top of the loop so that our move is now after the shuffle, that's great. Oh, we don't just need to shuffle, we also need to update our, it's only the left-hand side we need to update now, because the right-hand side is not in the picture anymore. So we need to shuffle, and then we need to update our yeah, left-hand side address location, this time just by a single element. We need to update it by. We shuffle. So basically both of these things, we're moving along one, you know, the register that has the result, and also our final location. And so then we can do the move. Okay, I think this should work. Okay, that's right, yeah, I did do this label index stuff. I think what I'm going to do is rename this to label and just have it cover everything. So we should get an error. Can't wait for the IDE, it's too slow. Oops, Yeah, so we only have one index to maintain, so it's probably up here as well. And then, you're so slow, IDE. Oh no, that is actually an issue because we don't pass the context in, I don't think. So let's go ctx gen context. And this is what we call it, so we need to pass the context in. Finally, this error appears. Okay. Did we fix that all up? Yes, okay. All the tests are still passing, but we haven't really, I don't think we've actually used this code yet. To use it, we need to do our tests on slices as well. So if we go slice 1 is basically just a slice of array 1, and slice 2 is a slice of array 2, and we do another plus equals, then we should find that slice 1, 0 is 5. And we get a lot of errors, a lot of assembly errors. Okay, let's have a look at what we got here. Okay, it looks like some dodgy formatting. So that is the multiply. Where is our multiply? It's here. We have only one operand here, which is the element size. That's what we're multiplying it by, but its limit location is what we're multiplying. Try that. 111. Okay. So this loop, because I'm doing %s where it should be %i for these indexes. I mean, not because it should stand for index, it stands for integer. Because that's what I'm putting into the format string. Okay, we get panic index out of bounds. Interesting. Let's have a look at that code again. Okay, I mean, slice 1 should have one element. Is there issues with doing that? Like if I do that explicitly? No, it still says index out of bounds. Okay. Let's see if we can find, I don't think this is the correct test. Let's disable our other tests for now. And then hopefully here we can see what's going on. That's the wrong test. Here we go. So we do all of our setup. Yeah, this is it. Here we have our loop. So this is setting up our variables, left-hand side address, right-hand side address. And this here is, ooh. I think this here is supposed to be setting up our limit location, but I feel like those are backwards. Where's our limit location? Here. Yeah. Yeah, I did think about swapping these around because it's a little bit confusing, like the source, destination, which that order makes sense to me, but in assembly, it's the other way around. Destination, source. So I had thought about swapping this so it was consistent, because right now it just got me there. Yeah, so we don't have, it still failed, but we don't have index out of bounds at least. Okay. Oh, task func? Oh, I'm looking at the wrong one. I think this is, because we still have one test, which is the comments, which is annoyingly difficult to get rid of. Yeah, this is it. Just because when I try to comment it out, there's like all sorts of comment conflict business. Okay, here we go. See, that looks better. Then we subtract 4 because we want the limit to be 4 elements back. Multiply it by 4, which is the size of each element. And we add, we shouldn't add this is adding the first value in the array, which is not right. We should be adding the address, actually. So the address. That looks better. So now R15 should be this address plus all of the array minus 4. So actually it should be like, in this case, because the array is only 1 element long, it should be like 3 elements back before it. So this comparison should be false right in the beginning, although again, I'm noticing this is R13 comparison should be with this. What's our other comparison? Okay, so we're getting somewhere. I'm seeing errors, and I think this is the wrong. So annoying. Can you just show me the right assembly? Okay, screw it. How do we? There, do that so it goes into a map that never actually gets used. I was probably looking at the wrong assembly. That's probably what it was. Okay, so 13 and 14 should have our addresses. So we copy from them into these. Then we say, okay, do we have enough elements to do this full copy of the 4 elements back to the source? If we do, let's do it and increment our addresses so we can loop around again and do it again. If not, we should go to the single loop. So that's what should happen here. So I mean, I guess as a test, we could like just comment out this whole thing. Just to simplify things for our case. Maybe we'll try that. So here's our this to this, I think. Yeah. So it still failed. So we just like copy everything in. Then we see we had subtracted 16 basically. So now we add the 16 back, so it should go to the end. So we should move 1 element, see have we got to the end. No, we have not. So if that is greater than that, if R13 is greater than, I guess it's greater than or equal to actually. Like that's the end. So if this has got to the end, well, if that's got to the end, we've gone too far actually. Interesting. If that's greater than that, then we're definitely in a bad place. If it's equal, that means we've just done a move that is to the wrong place still. So that's not good. Maybe this should be up the top. Yeah, because we've established that there's not 4 to deal with. There's less than 4. If it's 0, that's a bad thing. I don't think our code will be able to handle that. But let's say it's 3. Let's say it's 3, so the first one will go here. Then we'll see, okay, we're not at the end. Let me just, I do think this should be greater than or equal. What about this one here when we go to this loop? Greater than or equal to, maybe that's also greater than or equal. Let's see, hopefully we'll do enough tests that it will verify it. So we've got greater than or equal now. Then we need to shuffle, increment our address that we're going to, and go back up. So how did we do it actually in this code here? We basically have 2 conditions. We have one at the top and one here. And we do our increment at the end. So we do have one before the move and another one before the shuffle. So I guess we can just replicate that. I don't know if it's the most efficient, but hopefully it actually works. So we have, so this is the condition before the shuffle and the increment. This reminds me of an issue that we had up here, where if this was inside this condition, we had trouble. So we have to keep an eye on that too. So maybe this is not the best structure actually. Maybe that's the lesson to learn here. Or it's something that's easy here, but not actually that easy elsewhere. So this is like, okay. Oh, fuck you. I said rename. Let's call it limit, so it's kind of like consistent with what we had. Oh, do we even use it? We do. And this limit is like, this limit is like the actual end. So as long as we're less than the actual end, we continue. And if we're less than the actual end minus 1, then we do this. So if we go to, getting a bit lost, if we go to our assembly, maybe we'll just try to do the equivalent of that, although I feel like it's not the greatest efficiency-wise, but hopefully it actually works. So right at the top here, we want to say if the limit is greater than or equal to the left-hand side. Yeah, that's the opposite of saying this. I guess we could also say if the, well, we're saying the limit is greater than the location, the left-hand side. The limit is greater than the left-hand side. I just want to switch these around so that it's like the same as these. So left-hand side is less than limit. Left-hand side is less than limit. Yeah, I think I'm getting a bit confused about how this works. I'm pretty sure this is saying that this one here is less than this one. Left-hand side is less than limit. I probably had that totally wrong, and that's why we're getting so many issues. So left-hand side is less than limit. Yeah, that was probably a big problem. And now we're saying less than limit minus 1. So we need to make a new variable, which is limit minus 1. Yeah. So it's like, oops. It's like limit, I'll just call it limit 2. And we'll give it, we're using so many registers. Hopefully we don't run out of registers. That's a real problem that I'm worried about actually. So then limit 2 location. So when we do this here to update the limit location, what I'm going to do is copy the limit location to the limit 2 location. And then subtract from limit 2 location the element size so that it's 1 less. And then we should better put this down here. Wait, it's already here. But this one should not skip back to the end. It should skip to the Actually, what it needs to do is skip, just skip over this instruction. Yeah, so in assembly, this is not great. I have to make so many labels and stuff. I'm going to go with it, but I feel like we could later make this much nicer. So I'm going to call this the single loop increment, because this is where we kind of like do our increments, I guess you could say. And this is going to jump to and this needs to be before it. So, and that should be jump less than, I guess. So if the address is less than limit 2 location, no, if it's greater than or equal to the limit 2 location, then we don't shuffle. I'm not confident. I'm not confident. Yeah, we're using registers that we don't have. We've gone too high in the registers. Let's see if we can like restructure this in a way that it's a bit better. The tricky thing is that I don't want this to happen at on the last loop. We can do this first. Because left-hand side location is used there. Oh, but now, because we've already incremented it, we can do that same condition. No, because that condition is what prevents us from coming into here. Maybe if we had this at length -1, then we can do less than or equal to here. And here we have to do less than. But we're using the same variable. Yeah. Yeah, let's try that. So now we don't need our limit 2. So we don't need to do this. And this is, these are both limit location. But we need to make our, when we set up our limit, where are we setting it up? Here. That's the initial setup. Here's the, so this time we need to do 3. So we're not going all the way to the end. And if address location is less than or equal to limit, but this is, we jump if it's less than or equal. So actually we need to jump if it's greater, so it's the opposite. Because this is telling us when we jump, and this condition is telling us when we don't jump. You know, we continue. Jesus, this is crazy. And straight after this, we do our move, and then we do our increment. Right? We move into LHS location, and then we increment our offset effectively. Move into left side location, increment our offset. Now we check, is the offset less than limit? And if it is, then we shuffle. Okay. Otherwise, I guess we just go straight to the loop. Back to the loop, right? Skip shuffle. I guess that's basically what that's saying. So this is, so we want to skip the shuffle if limit, if location is greater than or equal to limit. Yeah, if location is greater than or equal to limit, then we skip the shuffle, we just go to the top of the loop, and we might just skip out at that point. Yeah, then we will skip out. No, we shouldn't skip out at that point. If we're skipping the shuffle, then we should do this, and then we should skip the shuffle again, and then we should skip here. Okay. Is this all correct? I mean, it looks good to me, but it fails the test. Let's have a look at actually what got generated. All of this looks good, I think. We kind of went over that. We copy our data into the things. I just realized we don't actually do we don't actually have this code. This is the code that does the actual operation. We never do that. Skip to single loop. Is that here? We move the data in. If we move the data in, we want to do the operation. I mean, come on, right? Yeah, we move it in, we do the actual add. That's nice. Now we add 12 to our limit. This is our limit. compare our limit to the current address, and if the current address is greater than the limit, then we go to the end. So this is the next statement. So in our case, our length is 1. So this is the length, I believe. So that should be 1, subtract 4, negative 3, times 4, negative 12. Negative 12, and then add to the address. So it's like the address minus 12, then we add 12 to it, so it's like the address now, it's like the start of the array. So these should be equal at this point because we haven't changed our 13. So this should not, we should not go here. We should move our stuff to R13, which sounds correct. Then we should add then we add 4. So we're at plus 4. So now this is greater than the limit. So we skip the shuffle. And we go up here instead. We compare again, and it is greater, and we come out. So I think that all looks correct to me, but we're getting a segmentation fault, which is not great. Where are we here? And it's really hard to know why. Is there anything that we can like cut out? I mean, if we just, I guess we can cut out a bunch of this stuff because really what we want to do is just this, right? So we could cut everything else out and just check that that is correct. I mean, it should be. So let's try it. So that's after single loop. Single loop. This move is the one we really want to do. How does that look? That's not happy. Okay. Maybe let's take this out. Let's just take out like as much as possible. We don't do any jumping even, so we could get rid of all the labels. So we can get rid of that. So I mean, like this is the real operation here. So we can actually get rid of all this 15 stuff as well. That's our limit stuff. Okay, so just this guy here is causing us issues. Oh, Well, that's a bit surprising. If I do that, does that work? No, well, of course the assertion fails then. Yeah, but we don't get an error. Like a, segmentation fault business. So this is all we're doing, we're just like taking the addresses. This looks totally legit. RSP plus 16 and RSP should be, when we're here, that should be these two. Should be the correct addresses. So these, they should be holding addresses. For slices, they hold addresses. For arrays, for slices, they hold. So for slices, this should just be a move. Let's try that and just see if I'm correct. Yeah, okay, that worked. So let's actually just maybe reinstate. I probably shouldn't do all of this at once. But if I reinstate like all of that, yeah, it's still working. Yeah, so this is interesting because we might be dealing with an array, we might be dealing with a slice. Do we know what we are dealing with? Is this node? Yeah, we can look at the type node that gets passed in. Okay. So in this case, it's like if type node dot value equals array, we do one thing. Otherwise we do another thing. So here we want to do the load effective address because the address, the array variable itself is where the data is. For here, I feel like it's good to do the copy. Here we want to just like copy this to this. This is the address. So, and I guess we use the unknown reference type. And we need to do the same thing for the right-hand side. So we just need to make sure these are all R's. What did I do wrong? Can probably tell in here. Well, that looks wrong. So I guess it's the second one I somehow messed up. I think I got them around the wrong way again, but I shouldn't be using those. Oh no, these are the ones that I'm using. Okay. Yeah, cool. All right. Sweet. So it should work for long arrays as well. I mean, we're gonna have to do I know our video has gone a bit long, but hopefully, fingers crossed, if I uncomment this guy, and I also try some slices with him, So that should be like 5, 10. Okay, add assign 2 has failed. Did I get these right? So slice 2 is 3 here, but we should add 2 to it, so it should be a 5. And this is a 6, and we add 4 to it, so it should be a 10 now. Only one of the assertions failed. It was one of the array ones. Okay, interesting. Let's have a look at the test. Well, because of the non-deterministic ordering, let's get rid of this, make sure we're looking at the right assembly. So this is where we're setting everything. Here's our first assignment. Oh, look at this. We are not shuffling. We should have shuffled in between these two. So we got our logic a bit wrong. So maybe this should still be here. That's kind of what I wanted to avoid, but yeah, I think maybe that should be there. Yeah, that's fixed that. But now if I reinstate these, I think maybe these are going to be wrong. Yeah, because now we need to replicate this logic down here. So here we're deciding whether to come into the loop. And if we do, then we do our move, but we don't do our increment yet. First we check whether we want to do our shuffle, and then we have our increment. If we want to skip the shuffle, then we go to this increment. Yeah, I think maybe that's it. Not defined, so this is actually where I'm defining the label. Okay, so this is good now, but when we come down to our loop, where is it? Here it is. So I have a feeling it's this part here. Yeah, I'm pretty sure this is all good. This is all good. Okay, so we come in, we check if we're greater than, if the limit is greater than the left-hand side. Let's have a look at our logic up higher. Limit is less than the left-hand side. We've said less than or equal. Limit is less than or equal. Yeah. So then we do the opposite to say that we're skipping out. Then we do our move, and then we do another condition. Do our move and another condition. So now if left-hand side is less than limit, so if left-hand side is greater than or equal to limit, then we don't go in. We go to here, otherwise we shuffle. Yeah, that makes sense. Then we do our increment and loop back up. So then we do our increment and loop back up. think that looks pretty good to me. I don't know what's wrong with that. It is some pretty tricky assembly. Very complicated assembly. Just make sure, I'm pretty sure we haven't affected those, yeah. Is at least one of them good? Oh, that one is good. But this one is not. So it was 6 here and we added 4. It should be 10. I feel like 10 is the right answer. But instead we get panic index out of bounds. Ah, because these slices are only 1 long. So now that should be the proper slice. Okay. Okay. Let me just double check that this worked now that I've changed the slices there. Okay, okay. All right. Okay, but this has been quite a long one, I know. But I think it's been some pretty in-depth assembly, right? So now I guess it's just a case of like adding 2, and here it is plus 6, so 16. Did I not reason that through correctly? Oh, 9 plus 6 is 15. Yeah, there we go. Okay. Okay, and this is the 4 element one. So now we have another one. It's 12 plus 8 is 20. Damn you. Ah, because we need to change the index as well. I hope that's why. Yep. Okay, good. So, but now I want to do a few more tests because I want to test with longer arrays. So here is a longer array. So I'm going to jump up to like, well, I guess anything above 4 is considered a long array, right? So let's just do all the way up to 7, 5, 6, 7, 8. Let's go up to 8. Okay. So these are 5. 4, and that'd be 10. So this guy would be 5 plus 10 is 15. And now if you add another 10 to 15, we get 25. So this pattern seems to be here, that it goes up by 5. Let's just check that that works. Ooh, it did not. Let's cut out the slice stuff. Okay, so this is the first time we've done a longer array. Let's even just cut that out so it's just a single. Okay. Interesting. I wonder if it's just this last element that's wrong. I thought it might be because we're going to have this loop, right? Lots of setup. And then we have this, we go into our loop. And this is where that doesn't look right for an array. There's a couple of assignments there. Oh, yeah, there should be lots of assignments. Yes, we're not doing any slice stuff. Oh, let's comment out these previous tests. We might have been looking at the wrong assembly. Looks like we probably were. So yeah, this looks better. So the length is 5. Right? Yeah, the length is 5. We know it's 5, so that looks good to me. I think RSP and RSP plus 20, so that's 5 back. Do I add? Oh, there is some assembly we still have commented out. What does that do actually? Oh, I feel like that's might be important. Skip to single loop if address is less than limit. Yeah, that's all this stuff. So we shouldn't go into here. This should skip us down to here. I don't really see how it should be. So now we're doing this load effective address. That's the only difference really for the arrays, and the length. So it's like getting this information is different, and everything else should be the same once we've got that. Yeah. But I guess with this test, this is the first one. I mean, I don't think that code that I put in is going to, yeah, fix that. It should be 10 plus 5 is 15. Since I've spent so much time on this, nearly an hour and a half, I hope that we're going to get this sorted. Why is that particular one not working? So it's the 5th element. So up to 4 elements seems to be fine, because up to 4 elements we were using this other code. But now that we're using 5 elements, the first 4 are fine. So we've copied our data in, we've done our add. So we should actually be doing 2 adds, shouldn't we? We should be looping around and doing this twice. Okay, so let's just reason through this. So the length is 5. We'll subtract 4, so it's 1. Times 4 is 4. So yeah, we'll just say that it's like relative to our left-hand side, it is 4. Okay, so now we do our copy and stuff, and we compare them, and the left-hand side should be less than, left-hand side should be less than that. Which means that we should loop around. We should move and loop around. We should do all this stuff if this is less than this. And it is. I'm trying to think what we should do if they're equal. I think if they're equal, we should also loop around. Because if they're equal, it means that there are 4 more to go. So it should be JG, I think. Is this it here? I think so, JG. Hey. I'm actually kind of surprised that worked. Okay, now we try the slices. Oh my God. That's so nice. That's so nice. Okay. We're almost there. Thank you for hanging in here. I'm actually quite stoked that we're managing to get this done, even though it's taking forever. So this goes up by 3, 18. This goes up by 5. Seems to be the pattern. Oh yeah. Okay, so I just want 2 more tests. I just want to go up to 8. I'm pretty confident 7 is going to work, but 8 is a bit of a different case. So 6, 7, 6, 14, 21, 35. Pretty sure that will work good. Okay. Now, 8 elements. So this is the one where it should just loop around twice. We might just check the assembly of this one as well, just to make sure it does do that. Oh, well, we don't know because it's a loop. We don't know just by looking at the assembly. 40. Is that right? All right. Okay. So if all of those are working, let's just uncomment the rest. So we have all of those add signs and they all work. And I'm just going to uncomment all of the tests. Just make sure all of our tests run. We'll run that once. Just scroll through here to make sure they're all good. Okay. Whew. What a beast, right? We haven't done any in-depth assembly like that for a while now. That's some of the most complex assembly I've ever written, I think. So I'm really stoked that works. And we have, there we go, vector math for all of our, for slices and for arrays of different lengths. What I've just become aware of is that we're only testing F32. We haven't tested F64. We probably should. And what's the other thing that I just realized we haven't tested? Haven't tested F64. I think there's another aspect of it that's not tested. Oh yeah, we've only tested plus equals. We haven't done minus equals, multiply equals, or divide equals. But I think this is a pretty awesome step that we've made. Pretty happy. So that's enough for today. Thanks for stopping by. Have a good one. Ciao for now.